Hello everyone, and welcome to the first of possibly many YouTube videos, depending on how many snowpocalypses we have. I hope you were all good at your house, digging out of the snow, trying to find a way to make it to school tomorrow, because I know you were all very disappointed to miss today. So anyways, what we're going to do today is we're going to go through the alternate examples that we did not get to today, and then of course tomorrow we will go over the study guide. Thursday you will have your test. So that is our plan for the rest of the week. That was for you, Shelby, because I know that you like having a set plan for everything that we're doing for the rest of the week. Hopefully this distance learning thing works out well for you. If anything, maybe it gives you some practice for college where you'll have things like this. Sorry if there's some noise in the background. I am in our office, which is like my podcast studio / my wife's work office. But the kids are kind of crazy, so you probably can hear them in the background licking windows and doing all the crazy other things they do. Anyways, without further ado, let's go ahead and get started. The first problem we have is the one on the Aussie Instant Lottery. So I'm going to write the title at the top just so you know what problem we are on. So the problem tells us that the Australian official lottery has scratch-off instant lottery tickets that can be purchased for $1. The probability of winning a prize is 1 in 4. Part A, it says, Mr. Urban is feeling lucky one day and decides to purchase 100 of the scratch-off instant lottery tickets. Find the probability that fewer than 20 tickets are winners. So the first thing we want to do is we want to ask ourselves, is this a binomial probability or something else? And the main thing that gives it away that it is binomial is the fact that there is a finite or a set number of trials, which is 100. Okay, so as we continue for part A, it is going to have a binomial distribution where our fixed number of trials is 100 and our probability of winning is 1/4. So that's kind of our information that we have given up front, and we are looking for the probability that y is less than 20. Okay, fewer than 20 is what it says. It doesn't say 20 or less, it says fewer than 20. So if we're talking about it in terms of the calculator, we're going to have to revert that to y less than or equal to 19. Remember, the calculator is always going to compute it as less than or equal to. So that's what you're going to put in your calculator. And since it is a less than or equal to, we are clearly going to do binomial CDF here. And our number of trials is 100, which we've already labeled it up above, but you know, let's be safe here. And probability is 1/4, and our X value is 19. And you get your answer, which would be 0.09953 if the textbook was correct in their solutions, because I left my calculator at home. So anyways, that's how you would do A. I think it's pretty cut and dry. I don't see that one being very hard. Again, I think the big thing with probability is going to be determining when it's binomial, when it's geometric, or when to do a tree diagram and those type things. But that one was pretty obvious in the fact that we're doing binomial probability right now. All right, so part B, it says, in fact, Mr. Urban won a prize for only 19 of the tickets. Does this result give convincing evidence that the probability of winning is less than 1/4? So this is one where you're having to talk about, is it convincing that he won a certain amount of tickets? So the answer they give, it says, if the probability of winning a prize is 1 in 4, there is a roughly 10% probability that fewer than 20 of his 100 tickets win a prize. Because it is plausible that he would win on only 19 tickets purely by chance, we do not have convincing evidence that winning is less than 1/4. And basically, no, there is not convincing evidence because that probability in part A is fairly high. It is a fairly high probability. Okay. But basically, this probability does not have a wow factor, and that's really what we want to focus on. Whenever it's convincing or not. If it has a wow factor, like, oh wow, that's only like 1% or less or something, then you might have convincing evidence for something like that, something strange to be happening. But there's really no wow factor in that. So there's no convincing evidence that it's higher. It's just kind of, it's not a super high probability, but it's also not a super low probability. So anyways, that is that. Let's go to the next problem. All right, so the next one has to do with coin tosses. And it says, Mrs. Patinaud asked each student in her AP Statistics class to toss a coin and record the result. There were 28 students in the class. Assume that all the coins are fair. Let X be the number of coins that landed heads, and it gives you a histogram of the probability distribution of X. So A, it says, what probability distribution does X have? So in this one, we're going to need to determine if it is binomial, geometric, that sort of thing. So is it binary? Yes, there's a clear success and failure, which is heads and tails. Okay. The fixed trials, yes, there are 28 students in the class who are flipping a coin, so that's there. And independent, yes, one flip does not influence another. Okay, if you get heads one time, you're not more likely to get heads the next time. So it is independent. And are all of them equally likely? Yes, they are all equally likely of heads. So therefore, it is going to have a binomial distribution with our n equal to 28 and our p equal to 1/2. Okay, so that one's that. And then part B, it says describe the shape of the probability distribution. And if you look at the histogram above, it is symmetric. And it has one peak at 14. Okay, so it's kind of like doing the cuss here, but not completely. It just wants you to describe the shape. So it is symmetric. That's pretty clear. It actually looks perfectly symmetric, which is kind of strange that it's perfect. But also include that single peak at 14, because you could be symmetric and have two peaks, or be bimodal, or trimodal, or quasimodal, or something weird like that. So anyways, yeah, just one peak. So symmetric doesn't really tell the whole story there on the shape, unless if you include that. So that is it for coin tosses. So we'll flip on to the next page. All right, this is more binomial coin tosses. And I'm sure it's going to build off the same problem. It does appear to be that way. So part A, it wants us to calculate the mean and interpret it. Okay? So the mean of X, remember that is N times P, which is going to be 28 students times 1/2, which is equal to 14. And our interpretation, what incarnation? Our interpretation, see, it's just like being in class. I still make the same stupid jokes. If the coin toss was repeated many times, with the 28 students, the average number of heads is about 14. Okay, somewhere in that range. You're repeating that trial of 28 students many, many times, and if you do it many times, the average number of heads is going to be about 14. So that would be your answer on that one. Okay, and standard deviation is part 2. So the standard deviation of the random variable x is, again, you just have pretty much a straight formula, np times 1 minus p, which is 28. The probability of succeeding is 1/2. The probability of failing is 1/2. Okay, much like the class that you're currently in, AP Statistics, which that's going to be 14. Half of 14 is 7. So the square root of 7 is, that's a big square root. Let's erase that a bit. Square root of 7 is 2.65. And of course, like always, we have to interpret this as well. And it's going to have the same kind of start. If coin tosses, I'm going to make that one word because I can, were repeated many times, with 28 students, the number of heads would be, I'm running out of room here, on average 2.65 away from the mean, which was what we did in part A. And I'll go ahead and mention that. Sometimes they might count off for not mentioning that. Okay, so again, mean is the average number, the expected number you would expect to have that many heads. Okay, it's just like expected value. And standard deviation is, if you did it many times, that is on average how far away you would be from the mean. So if you did it many times, your amount of heads would be on average 2.65, either less or more than the mean. So that is that page. Okay, next one has to do with Facebook, which is funny because we were originally going to do this via Facebook Live, which we decided against it because we don't trust Mark Zuckerberg. And I don't remember who it was who said that, but you probably have a good point, and you're probably smarter than me than wasting time on Facebook. Okay, so this one has to do, again, with teens and Facebook. It says a recent report from the Pew Research Center estimates that 71% of teenagers aged 13 to 17 use Facebook. Assume that the claim is true. Suppose that some researchers are going to contact a random sample of 300 teenagers to find out if they use Facebook. Let X equal the number of teens in a random sample of size 300 who use Facebook. And at first on A, it says explain why. Explain why X can be modeled by a binomial distribution even though the sample was selected without replacement. And the reason why is because you have that 10% condition. So 300 is less than 10% of all U.S. teens. Okay, so you can look back at the notes there whenever we talked about that 10% condition. You can, if you have something like that, then you can use binomial distribution, even though it is, even though it's selected without replacement. So, you know, you're pulling them out and keeping them out, which essentially is, it means that they are not independent of each other. Each trial is not independent. So since each trial is not independent, but you have a large enough sample size, then you can do that. Okay, so then part B, it says use a binomial distribution to estimate the probability that 200 or more teens in the sample use Facebook. So 200 or more is going to be X greater than or equal to 200. Okay, because it's easier, we want to convert this to using the calculator, which is going to be 1 minus the probability that X is less than or equal to 199. Remember, calculator always has to be less than or equal to. Okay, if you're going to use the calculator, which I would recommend because it's really easy. And of course, it's less than or equal to, so that's going to be CDF. Okay, we're not looking at 1 point, we're looking at several points added up. So binomial CDF, our trials is 300. So I'm going to label that, cover our bases. Our probability is 71% of succeeding, and our X value is 199. And whenever you type that in and do 1 minus that, you get your final answer of 956. So 95.6% that more 200 or more students randomly chosen would use Facebook, which sounds about accurate. I would probably agree with that. Okay. All right, so that is that one. That was pretty easy. Just had that little trick there on part A that might throw you off a bit because we didn't discuss a ton of that. So, make note of that. I don't think there's anything like that on your test. I could look back at it and let you know, which we'll discuss tomorrow, since I'm pretty sure we're going to be in school tomorrow. All right, so we got, I think, 2 more. Teens are still on Facebook. Mark Zuckerberg has us. Okay. Recently, the Pew Research Center, same stuff there. In A, it says, justify why X can be approximated by a normal distribution. Okay. So this is the large counts condition. Is N times P greater than or equal to 10? And is N 1 minus P greater than or equal to 10? Well, N is really large, 300 times 0.71 is greater than or equal to 10, and 300 times 0.29 is greater than or equal to 10. So we're good on both accounts, therefore we can use a normal distribution. All right, so part B, use a normal distribution to estimate the probability that 200 or more teens in the sample use Facebook. So we need to find our mean, which is NP. So that is 300 times 0.71, which we actually did earlier up here, and we get 213. We have to do our standard deviation since we're doing a normal distribution here, which is the square root of 300 times 0.71 times 0.29, and that gives us our answer of 7.859. And it wants us to calculate the probability that 200 or more teens use Facebook. So you got your little normal curve. Okay, 213's in the middle, and you're going 200 or more. Okay, so now that we're using a normal distribution, we are actually going to do normal CDF, not binomial CDF, okay, because it specified to use a normal distribution. Our lower limit would be 200. They had something really weird printed on here, and I didn't, but then I saw the right answer. So there's our lower limit. Our upper limit is a bagillion. Our mean is 213. And our standard deviation is 7.859. Okay, and you get your answer, which would be 0.9510. Okay, so a 95.1% chance that more than 200 would be using Facebook, which whenever we did that same problem using binomial, we were very, very close to that. Okay, so you can kind of see the line up there based off of however you do it. Okay, and we have one more question here on the alternate examples. I'm assuming this is probably going to be a geometric probability because we haven't done any of those yet. Play until you win is the name of this exercise. So we're looking back at the Australian Lotto again. And A, it says, find the probability that Mr. Urban buys exactly 8 lottery tickets in order to win. So we do not have a fixed trial, so this is clearly going to be geometric. Okay, and we are looking for the probability that it is exactly 8 until he wins, which you could do GeoPDF because it's an equal to. Okay, it's actually geometric, but I think we could shorten that. And our number of, well, we don't know number of trials. So our probability was 1 in 4, and our X value is 8. Or you could actually just use the formula because it's pretty easy. Your probability of not winning is 3 in 4, and that's going to be to the 7th power times 1/4, and you get the same answer either way, which is 0.0334. So a 3.34% chance that he would not win until his 8th ticket. Okay, Australia, I guess they like to give away money because I've bought 8 lottery tickets before and won nada. So anyways, I guess it's an instant win, those scratch-off tickets. I have won those before. You know, you win like 2 cents and you're like, I just want another ticket, and you just keep scratching all day. I guess y'all are too young to do lottery tickets, so maybe y'all don't understand that. All right, anyways. Okay, so part B. Find the probability that x is greater than or equal to 5 and interpret this value in context. Okay, so you're doing the probability that x is greater than or equal to 5. So basically, what would it be if it took him 5 or more chances to win? Okay, which is going to be 1 minus the probability that x is less than or equal to 4. Remember, calculator, you want to go less than or equal to. All right, so you're going to do 1 minus geometric. This is going to be CDF because we're accumulating 1, 2, 3, and 4. Okay, and in their notes, they actually do this. They actually listed out all of the possibilities. I don't know if that's really necessary, but they did list it out that way. And the probability of winning is 1/4. The number of trials here is 4 because that's where the less than or equal to occurs. So P in trials, and we end up getting 1 minus 0.6836, which is 0.3164. And it wants us to interpret that value in context, and that basically means there is about a 32% probability that Keith Urban, Mr. Urban, I bet that is because he's from Australia, so I'm sure that is like a play on Keith Urban. Anyways, so there's a 32% probability that he will buy more than 5 before he wins. Okay, so the 32% probability that he'll have to buy 5 or more before he wins, and obviously a 68% probability that he would win before that. Okay, all right, that wraps us up on the alternate examples. I hope I didn't just waste 30 minutes of my time going over that, and y'all actually take advantage of it and use this thing to help you for your test on Thursday. I will see you all tomorrow. Bye.